Hi, our topic for today is about integration of trigonometric functions. At the end of the lesson, you must be able to be familiar with the integration formulas involving trigonometric functions and perform integration involving trigonometric functions. To evaluate integrals involving trigonometric functions, so we will use the following basic formulas. So recall that the differential of cosine u is negative sine u du. So when you multiply by negative, so we have sine u du. So therefore, the integral of sine u du is negative cosine u plus the constant c. Also, if you can recall, the differential of sine u is cosine u du. So when you get the integral of cosine u du, we have sine u plus the constant c. For the third formula, now we obtain this by getting the differential of tangent u. Recall that the differential is secant squared u du. So when you get the integral of secant squared u du, this is equal to tangent u plus the constant c. Also, when you get the differential of cotangent u, you have negative cosecant squared u times negative. So you have positive cosecant squared u du. So therefore, when you get the integral of cosecant squared u du, we get negative cotangent u plus the constant c. So you do the same for the rest of the formula. No? We can define the integral of this trigonometric function. So the fifth formula is the integral of secant u tangent u du, which is equal to secant u plus the constant c. Again, when you get the differential of secant u, you have secant u tangent u du. Therefore, when you get the antiderivative of this function, you get secant u plus the constant c. The next formula is the integral of cosecant u cotangent u du, and this is equal to negative cosecant u plus the constant c. Next, we have the integral of secant u du is the natural log of absolute value of secant u plus tangent u plus the constant c. Next formula, we have the integral of cosecant u du is equal to the natural log of absolute value of cosecant u minus cotangent u plus the constant c. Next, we have the integral of cotangent u du is the natural log of absolute value of sine u plus the constant c. And then the last but not the least is the integral of tangent u du is negative of the natural log of absolute value of cosine u plus the constant c, or this is also the same as the natural log of absolute value of secant u plus the constant c. So before you evaluate any integrand involving trigonometric function, make sure that you have memorized all these formulas. Okay, to see how those formula can be applied, let us solve the following problem. So suppose we are asked to evaluate the integral of 1 plus sine x dx over cosine x. So if you look at the integrand, this is not integrable using any of this formula. So what you have to do first is simplify this. You divide the numerator by the denominator. So you have 1 over cosine x plus sine x over cosine x times dx. But recall that 1 over cosine x is secant x, no? Because the reciprocal of cosine is secant, or vice versa. And then sine over cosine is tangent x, and then you apply distributive property. You distribute the integral sign together with dx to each of these terms. So we get the integral of secant x dx plus the integral of tangent x dx. But the integral of secant x dx is equal to, using this formula, the integral of secant u du is the natural log of the absolute value of secant u plus tangent u plus the constant c. So where the value of u here is x and your du is dx. So applying that formula, the integral of secant x dx is the natural log of absolute value of secant x plus tangent x plus the integral of tangent x dx. Using the last formula, we have the negative of the natural log of absolute value of cosine u plus c, or you can use the last formula or the second formula, which is the natural log of absolute value of secant u plus the constant c. So for tangent x dx, your u is x, and then your du is dx. And then applying this formula using the second, the integral of tangent x dx is natural log of the absolute value of secant u, where u is x, plus the constant c. So the final answer is natural log of absolute value of secant x plus tangent x plus the natural log of absolute value of secant x plus the constant c. Okay, so let's solve the second example. Again, suppose we are asked to evaluate the integral of 1 plus cosecant quantity raised to the second power dx. So if you look at the integrand, because the exponent is 2 and there's no direct integration formula appropriate for this type of integrand, so what you have to do is you expand. You take the square of 1 plus cosecant x. So when you take the square, you have 1 plus twice the product of the first and the second. You have 2 cosecant x plus the square of the last term, which is cosecant squared x dx. And then by distributive property, you have the integral of 1 dx is integral of dx plus the integral of 2 cosecant x dx. Then we factor out 2. So we have the integral of cosecant x dx plus the integral of cosecant squared x dx. But from the basic formula, recall that the integral of dx is x plus 2 times the integral of cosecant x dx. For cosecant x dx, recall from this formula that the integral of cosecant u du is the natural log of cosecant u minus cotangent u plus the constant c. So in this problem, your u is x, and then your du is dx. So applying this formula, this is equal to the natural log of cosecant u, where u is x, minus cotangent u, where u is x, minus the integral of, or plus the integral of cosecant squared x dx. But from the formula, recall that the integral of cosecant squared u du is negative cotangent u plus c. So here your u is x and your du is dx. So applying this formula, we have negative cotangent u plus the constant c, but your u is x. So the final answer is x plus 2 times the natural log of absolute value of cosecant x minus cotangent x minus cotangent x plus the constant c. Okay, so let's have another example. Suppose we are asked to evaluate the integral of e to the 4x sine of e to the 4x plus 1 dx. Observe that this is a combination of exponential and trigonometric. But if you look at their arguments, the argument of sine is more complicated than the argument of the exponential function. So in choosing your u, you choose the one with the complicated argument. So in this case, we let u be the argument of sine, which is e to the 4x plus 1. And then getting the differentials of both sides. So du is the differential of e to the 4x is 4e to the 4x dx. Then differential of 1 is 0. And then you compare this differential to the integrand, whether this is part of the integrand or not. So as you can see, e to the 4x dx is part of the integrand, but 4 is missing. So you have to remove this by dividing both sides by 4 to get e to the 4x dx is du over 4. And then by substitution, we can now replace this e to the 4x plus 1 by u. And then this e to the 4x dx by 1/4 du. And then you factor out 1/4. So we have 1/4 times the integral of sine u, where u is e to the 4x plus 1, times du over 4, which is e to the 4x dx. But recall that the integral of sine u du is negative cosine u plus the constant c. And because there is this constant coefficient, so this should be negative 1/4 cosine u plus the constant c, where u here is e to the 4x plus 1. So therefore, the final answer is negative 1/4 cosine of e to the 4x plus 1 plus the constant c. Okay, so let's have another example. So suppose we are asked to evaluate the integral of x e raised to the natural log of cotangent x squared dx. But we can simplify this by applying the properties of logarithmic function, wherein the base of the exponential function is the same as the base of the logarithmic function. And this is equal to the argument x of the logarithmic function. So applying this property, we can reduce this e raised to the natural log of cotangent x squared as cotangent x squared times x dx. Okay, but cotangent x squared is, you can integrate this by using this formula, that the integral of cotangent u du is the natural log of absolute value of sine u plus the constant c, wherein we let u be the x squared, and then taking the differentials of both sides, so du is 2x dx. And then if we look at the integrand, x dx is part of the integrand, but 2 is missing, so you have to remove 2 from this equation by dividing both sides by 2. So we get du over 2 is x dx. So now, by substitution, we can replace x squared by u, so you have cotangent u, and x dx as du over 2. But because 1/2 is constant, so we factor this out, so we have the integral of cotangent u du. But recall that the integral of cotangent u du is equal to the natural log of absolute value of sine u plus the constant c. So therefore, we have 1/2 times the natural log of the absolute value of sine u plus the constant c. But since the value of u is x squared, so the final answer is 1/2 times the natural log of sine of u, where u is x squared plus the constant c. So in summary, we can say that trigonometric identities and differentials are essentials in understanding the process of evaluating integrals involving trigonometric functions. Also, knowledge of u substitution method is also an important key in evaluating integrals involving trigonometric functions.